Again, welcome to Data Structure and Algorithm. This is CS435 class. In this lectures, we will cover the searching algorithms. Two major searching algorithms, which are the linear search and also the binary search. So first we start with what is searching. So searching is the process of finding a target or a search key element among a group of items, which we call the search pool, or determine that it isn't there. So again, an example would be, we have a list of items, let's say 7, 8, 10, and we are searching for 2. So the search key will be 2, and the search pool will be the 3 values. So our goal again is to do comparisons. And so this requires continuous comparing the target or the search key to candidates in the search pool. So an efficient search performs no more comparison than it has to. So again, in computer science algorithm, if we are looking for an item or searching for an item, the only option is to compare the item to the search pool. If they are the same, that means we find what we are looking for. If we go through all the items and we couldn't find any item that is the same as the search key, that means it doesn't exist. So we are going to define the algorithm such that they can search any set of objects. So the type will be generic type. And also we are going to implement comparable interface. Also, we are going to use the method compare to. Again, in Java, compare to return 0 if object 1 is the same as object 2. Now, if object 1 is greater than object 2, then it's going to return a greater value, a positive value. If object 2 is greater than object 1, then it's going to return a negative value. So here we say this call return a number less than, equal to, or greater than 0. If object 1 is less than object 2, then it's going to return a value less than 0. If object 1 is greater than object 2, then it's going to return a value greater than 0. Then if object 1 is the same as object 2, then it's going to return 0. So those are the two main things we are going to use in our coding using Java: comparable interface and also compare to method. So first we start with the linear search. Here we say the linear search simply examine each item in the search pool one at a time until either the target is found or until the pool is exhausted. So in linear search, we always start from the beginning and we compare the search key with the first item in the list or an array. So the example of a diagram here, we can see the starting, we are starting from the first item. So we compare the search key with the first item. If it's not the same, then we move to the second item. If it's not the same, then we move to the third item, etc. Again, when we find the item we are looking for, let's say the fourth item, the search key is the same as the element or the value in the fourth place, then we are going to return the location of the item, or we are going to say the item exists in the search pool, or in this case, in an array. Here we say this approach does not assume the items in the search pool are in any particular order. So in linear search, we don't sort the items in the list or the array. Now with binary search, one condition is the items in the array or the list must be sorted. But with linear search, there's no need. So this is the Java implementation of the algorithm. So again, our method name is linear search. The returning type is Boolean. So if we find the item, we are going to return true. If we don't find the item, then we return false. Now the argument or the parameters, we are using array here. So we have array named data, and also the data type is C, which is the generics. The variable main is represent the starting of the index of the array, the minimum index. The variable mass will represent the maximum index, the last index of the array. And the item that we are searching for will be the target. Again, the data type is T, which is again using generics type. So here we assign the mean to our index. This will be again array. We assume this is the array index. And the most important also, we have our flag variable found. We initialize it to false. So here we say why not found, which means if it's true, not false is true. And also index is less than or equal to mass, which means we haven't reached the end of the array. So if found is true and we haven't reached end of the array, then we can compare the items. Again, we start with the first items, so the index will be 0. So the data of the first item, we are checking if it's equal to the search key or the target. The search key is stored in a target variable, so target. Now, if this condition is false, then we increment our index. Then we check our Y condition again. Not false means it's true. If we haven't reached the end of the array, then the index will be less than or equal to mass. If index is greater than mass, that means we have reached the end of the array. So that will be false. We stop. Now, if the item is found, then true is found now. So the variable found will be true. Then if we come to the for loop, not true will be false. So the loop will stop. Then we're going to return true to the linear search method. So we can see the algorithm is here. What this means is that we start from beginning and then we compare the search key to the element from beginning. Anytime we find the item in the search pool, or in this case, the array, then we stop. So the while loop will terminate. So now let's move to binary search. As we said earlier, with the linear search, the list of the items is not required to be in any order, whether ascending or descending. But with binary search, we always have to make sure the search pool is sorted. Most of the time will be ascending order. So if the search pool is sorted, then we can be more efficient than a linear search. So this will take us to using binary search, because binary search always eliminates the large part of a search pool with each comparison. Actually, to eliminate half of the search pool with each comparison. And we shall see that in a few slides to come. So now, instead of starting the search at one end, we normally begin at the middle. So the algorithm of a binary search is that first, the items must be sorted. Second, we find the middle value. Then we compare the middle value with the search key. If the middle value is greater than the search key, then we'll go to the lower side of the items in the array. So which means half of the items we don't need to compare, will be eliminated. The upper side, the middle to the end, will be removed. Now, the other way, if the search key is greater than the middle value, then we are going to eliminate the lower part up to the search key. Then we search the upper side. So the best is to use the diagram here. So these items here are sorted. The first thing, we find the middle value, so we start from the middle. We compare the middle value with the search key. If they are the same, then we match. We return true. We find it. If not, we look if the search key is greater or lesser than the middle value. From the diagram here, it shows that the search key is greater than the middle value. So we go to the upper side. Then we repeat the same process. We find the middle value and we compare the search key with the middle value. If it matches, then we stop. If not, if it's greater, then we go to the upper side. If it's lesser, we go to the lower side. So in this case, from the diagram, it's lower. The search key is lower than the middle key or the midpoint. So we go to the lower and then find the middle. Then next, the search key is greater than the new midpoint. So we go to the upper side. So let's see an example here. Here we have a list of items from 8 to 88. These items are sorted. Now we want to find out if 29 is in this list. So the first thing we do is to look for the middle value. The middle value will be 54. We compare 54 with 29. We find out that the midpoint is greater than the search key. So we have to search the lower part, the left side of the 54. So here also we'll repeat the same process. We need to find the middle value. The middle value is 22. We compare 22 with 29. We find out 29 is bigger, which means the search key this time is bigger than the midpoint or the middle value. So we have to go to the right side. And the right side, we have 29 and 36. And so next, we find the 29. So here again, we say first compare the target to the middle value 54. We now know that if 29 is in the list, it should be in the front half of the list, that's the lower part. With one comparison, we have eliminated half of the data. And this process keeps going. Every comparison we do, we are going to eliminate half. That's why, again, the algorithm is called binary search. By means 2, we divide it to 2, half will be gone. So a binary search algorithm is often implemented using recursive function. So for each recursive call, searches a smaller portion of the search pool. And with each recursive call, half of the item will be eliminated and we search the other half. Either it will be lower part or upper part, depend on the value of the search key, if it's greater or lesser than the middle value or the midpoint. So let's see the implementation. Again, our method name is binary search. It takes 4 arguments. That's the array name and the type is T, generic type. The mean here represents the minimal index and the mass represents the maximum index. Again, this is array implementation. Target variable will be what we are looking for. We are searching in the search pool. So the first thing we do here again, we set our flag variable found to false. And we look for the middle value. Again, here we are assuming the items are already sorted. So we take the middle value, which will be the mean index plus mass divided by 2. Now, if we get the middle value, which is now stored in a midpoint variable, we are going to compare it to the target. So here we have if array name data midpoint dot compare to target equal to 0, then we assign true to found, because we say compared to, if the value is 0, it means the item we are comparing are the same, the midpoint and the target. Else, if the data midpoint dot compare to target greater than 0, which means this time the midpoint value is greater than the target, the search key we are looking for. So if that is the case, then we have to look the lower side. So that's why we say mean less than or equal to midpoint minus 1. So the lower side we are looking at. So we are looking at the lower side, we recursively call our binary search method with the 4 argument, the data, but we are starting from mean. Again, since the search key is greater than the midpoint is greater than the search key, we are starting from mean. We're looking at the lower side. And here we say midpoint minus 1 because excluding the midpoint value. As we can see here, the example, the previous example we have. Now, if the middle value is 54 and I'll go to the lower side, the search key 29 is less than 54, then I'm going to search from 8 to 36, excluding 54. So that's what we mean by midpoint minus 1. Now, here we said else. Here we are saying that the midpoint is greater than the search key. The last option means the search key is greater than the midpoint, so which means we have to go to the upper side. So excluding the midpoint, so we start from midpoint plus 1 to the mass. That will be the upper side. Then recursively call the function. Then we'll return the found. So this found can be either true or false. If any of these 3 conditions were met, then it's going to return true. If none, then the item is not in the list or the array. So the comparing both linear and search algorithm, we know linear search, we compare from beginning to the end. So n will be the size of the array n. So this means the worst case, we are going to have a big O notation n. The best case means the item we are looking for is in front of the array, the first item in the array. So that's like big O1, the best condition. So in general, average or expected, we'll say the expected case should be n by 2, half of it. So this takes us big O notation to be n. Now with the binary search, the worst case, since we are dividing by 2, ignore half of it every comparison. It will be log base 2n divided by 2. So a very good algorithm again will be big O1. In this case, if the middle value is what we are looking for, we do only one comparison. Other than that, the best will be log base n, big O n, log n. So log n, again, is better than n. So that will be the conclusion of search algorithm. Again, these lectures, we went through the linear search and also the binary search. So again, wish everybody the best and see you in the next class.